Hello everyone. So we're going to talk about topic of confidence interval, central limit theorem. This is like a review session for next chapters we have. It's very important to make sure that everyone is on the same page when it comes to central limit theorem and confidence interval topics. So please pay attention and feel free to ask your questions. So why do we need to understand what the confidence interval is and what does it actually mean? So the main problem comes from the time that we don't have access to all population data, or it's very costly to have we have a lot of errors involved when we use population data. So as a result, what we do, we collect a sample. And I told you before that collecting a sample is very important. Sample has to, in fact, shows the behavior of population. So the sample should follow what population shows. And statistically speaking, we can say those statistical measures that you take from the sample should represent or be close to the actual values in population. So let's see what we have here. To contact the whole population would be time consuming or costly or sometimes impossible. So the cost of studying all items in the population may be a lot, right? As a result, we look for samples. What is a probability sample? So probability sample is a sample selected such that each item or person in the population being studied has a known likelihood of being included in the sample. So when we talk about error in statistics, what we actually mean is the difference between the actual value and actual parameter, statistical parameter versus what we estimate, right? So when we say estimate, we mean the sample's parameter. So that parameter can be average, it can be standard deviation, variance, and many other statistical measures. But majority of times that we're talking about this parameter, we're talking about average and standard deviation. So a sampling error is the difference between a sample statistic, in this case we're showing average, and its corresponding population parameter. So you can see X bar represents average of the sample, and mu, the Greek alphabet, shows the population's parameter. So it's like the whole class average grade is like 92%, but this sample I select might be 89 because I used less cases, and some cases are missing. As a result, the numbers may not actually show exactly what it is. So that difference is what we consider as, that difference is what we actually consider as, I can say, the error, the sampling error. So, of course, the higher this error, the higher the probability of some kind of mistake or problem or error in your decision making in the future. So to reduce that mistake, to reduce that amount of error in decision, you need to make sure your sample has values close to the population. So you don't want to have a case that the sample and the population have very different parameters, right? So X bar is estimated. Why is it estimated? The estimated value because it's an estimation for the population, because many of those values, cases, are missing when you have a sample. The sampling distribution of a sample mean is a probability distribution consisting of all possible sample means of a given sample size selected from a population. So sampling distribution of a sample mean is a probability, right? It's a probability of distribution consisting of all possible sample means. So here we have a very short example, and you can see we have a sample of employees with associated earning salary per hour for each of them, right? So $7 for Joe, Sam, $7, $8. So what a sample mean looks like if I want to select a sample mean with a sample size of 2. So I would select samples of 2 by 2. Let's say Joe and Sam, Sam and Sue, Joe and Sue. So any combination, right? Any combination of the two of these can create a sample mean, right? And we can get the average of that sample. So if I say my sample 1 is Joe and Sam, they both earn $7 an hour. So in average, how much they earn? $7 because they're not different. But if I take Sam and Sue as a sample, the sample mean will be 7 plus 8 divided by 2, which is 7.5, or the middle of 7 and 8. And that can continue for all of these. So for example, if I say one of the samples is Sam and Ted. So Sam and Ted, 7 and 9. The average of 7 and 9 is 8, right? So what's the population mean? So the population mean, you can add all of those in the population and divide by total. What's the sampling distribution of a sample mean for sample size of 2? So we can calculate that, right? We can actually, every 2 of these can create 1 sample. And that's our, for each one, each group, each sample we take, sample of 2 we take, we can calculate the average, and that would be the sample mean. What is the mean of the sampling distribution? So if you calculate the average of all these averages, then that would be the same as the population's average. What observations can be made about the population and sampling distribution? So we can find out first. So if you have all the population values, the population mean will be 7.71. And we just add all numbers divided by how many cases we have. All right, so this is an example of the sample means we collected. So Joe and Sam, Joe and Sue, Joe and Bob. So Joe with everyone, and then Sam with everyone, right? And that continues until Art and Ted. And for each one, we know the hourly rate for each person, and then we can calculate the average mean. So for sample 1, we have average of 7. Sample 2, average of 7.5. And that continues to the end. How many samples could we select in this case? 21, right? This combination of 2 by 2, that, what makes this a combination? It's not a permutation. I told you, permutation, order matters. In combination, order doesn't matter. So when we say Joe and Sam, so this sample is the same as Sam and Joe, right? So it doesn't matter who is first. That makes it a combination. It doesn't matter who is first, who is second. The position doesn't really matter, right? As a result, we call it a combination. That actually reduces the cases. So if we have Joe and Sam, later we don't have Sam and Joe, okay? So this is the original population values. And you can see that in the population, we have, in fact, abnormal distribution of data. After selecting our sample mean, we have actually somehow have a better normal distribution, right? So can we make this a better normality? Yes. In this case, we have size of the samples are 2. If you increase the number of samples to 3, 4, that would make a better shape of your sample size, or sample distribution. So as a rule of law, central limit theorem will explain, and we can actually provide a proof that average of these sample means, that mean, back up, these averages. If we get average of all these averages of each small sample, average of these small samples of 2 will be equal to the sample to the population average. So what's the population average? 7.71, right? So we have 7.71. This is in fact average of those smaller samples. So you can see that they are equal. But is this the same for standard deviation or variance? So you know that variance is the square of standard deviation, right? So this is the variance. Variance of those small samples of 2, is that equal to the population's variance? The answer is no. It's equal to the population's variance divided by n. So I get a radical on both sides. What's more important for me compared to variance is the standard deviation. So I get a square root on both sides. That gives me standard deviation. So standard deviation of these smaller samples will be equal to standard deviation of the population divided by radical n. So that's where the radical n comes from. Because originally the formula for variance is divided by n. So when you get the square root, that becomes radical n. So does it matter the original population or the original sample we select has actually a normal shape? The answer is no. Whatever the original shape of the population, this is the population's shape of distribution of the population, right? Maybe it's like this, maybe it's like this, right? But when you start selecting those sample means, size of 2, you have a shape close to normal. If the size of sample increases, that gets closer to normality. And the larger the size of that sample mean, you can actually get a perfect population. In fact, sample mean that is perfectly normal. Okay. So one more time, when you have any different type of population distribution, when you select your sample distribution or sample means, the larger the size of your sample mean. In the case we just saw, we had the sample mean size of 2. If you have size of 6 or especially 30 or more than 30 samples in each case, each sample, then you can have a perfect normal distribution. Okay. So in fact, what sample mean does, other than just giving us more informative values, is that's the main thing that it does for us. It normalizes our data with the same average, with the standard deviation difference of dividing by radical n. So that's very important for us, because if we have any population that is not normal, we can actually normalize it. Why normalizing our data is so important to us? Normalizing our data is important because many statistical hypotheses, many statistical methods are actually designed in a way that they work for normally distributed data. As a result, when you have an abnormal data and you want to use it to conduct a certain research and use certain method, statistical method, then that statistical method has a requirement. Not all of them, but many of them might have requirements such as your data has to be normal. And normally distributed data is actually much better. It reduces the amount of error in your whole calculations. Okay? So formulas we use, if you remember from the past, converting your distribution of your values from x to z. So previously it was z equal to x bar minus mu over sigma. Now, x bar is the same. When you have a sample mean, this is for a sample mean, right? For a sample mean, x bar is the same as the population. But what's changing is sigma is changing to sigma over radical n. That's what we just went over, right? So this sigma is replaced by this sigma of the population that you learned before. But this time we have sigma over radical n. Why? Because this is from a sample mean of size n. In the example we just saw, n was 2, meaning that each sample we selected had 2 Ks. So we use this formula to actually calculate the z value. So The same thing goes with go for the t-distribution. I hope you remember that t-distribution is a distribution very similar to z-distribution with a difference. They both look like a bell shape. They are both symmetrical, but the height of the center of z-distribution is slightly higher than the t-distribution. And remember that for cases that you have more than 30 Ks, actually T and Z distributions are replaceable. So you don't have to use the T if you have more than 30 samples in your sampling. Another example we have here, a bar manager claims that her weekly profit is $12,000, standard deviation of $1,000 per week. So they are making $12,000 in average every week, right? A standard deviation of 1,000. So when you see this, immediately you need to remember what you learned in the past about standard deviation. With these numbers, you can actually calculate very quick and say what portion, approximately what portion of your samples of your different weeks, the range of your average profit would be, right? If one standard deviation away from the mean, 68%. 2 standard deviation, 95%, right? So that means, let's say for 95%, 2 times 1,000, 2 times standard deviation away from the mean. So that's $12,000 plus 2,000 minus 2,000. So 95% of your weeks, you should earn somewhere around 10,000 to 14,000. Does that make sense? So if the profit is normally distributed and a random sample, now we are taking a sample mean, right? That was for the whole population, but now we have a sample mean of 25 weeks of profit. So what's the probability that the sample mean will be? For example, let's take one of these and the rest you can practice at home. Less than 12,500. So we had a formula and all the information is given to us, right? So we know the average, we know the population and standard deviation, we know the sample size. That's all we need. We have all the numbers and we have the sample average, 12,500. So we can simply just calculate that, right? So we can, let me just show you really quick how that calculation goes. So saying 12,000 is the average profit with $1,000 of standard deviation and sample size is 25 weeks. That's our sample size. And we also have, so we had one more information here, and that was, what's the probability the sample mean would be less than 12,500. So question is, probability that the sample mean is less than $12,500. We can easily calculate that. So the formula was Z equals to X bar minus mu, X bar minus mu, and divided by sigma, right? Standard deviation over radical SQRT of n. That was our formula. If you remember, we just saw it. Okay, so let's just replace the numbers. So we have X bar. In this case, which one is X bar? This is our X bar. the sample size of 25 weeks. We want to see what's the probability that the earning is 12,500. So we have 12,500 minus 12,000 divided by, and here we have, so sigma is actually given 1,000 over 20, radical 25, which is 5, right? That's, if you calculate that, and let's really quick calculate this. So this is 500 difference divided by, so that would be like 200. So that's 2.5. So there are different ways to use the 2.5 to calculate your probability. One way is using the Z distribution or Z table. So we don't want to use the Z table. Let me really quick show you here how to use a Microsoft Excel. Okay. So we want to use the 2.5, right? Z distribution for, so Z of 2.5, and we want to calculate the probability of Z to be less than 2.5. What is it? 2.5. So it's actually, we can click here, say it's equal to, and on the other side we can calculate it. So that would be, so what Excel does can actually give us the less than, right? It always gives us the less than. So you just type a norm and a couple of different values come up. So let's see which one help us. So this is the standard Z. It's not, it's a standard Z, so you have to use the one norm.s. And there are two types, standard distribution and inverse. So the inverse, let's see if this works. So inverse just needs the probability, so that's not the one. So we just use the distribution. So it's asking for Z. Z is 2.5. And it's also asking, do you want cumulative or non-cumulative? So what's the difference? The difference is for normal distribution, which is continuous, for any distribution that is continuous, you use cumulative or true. So click on true. If it was a probability that is not continuous, then you would go for false. So for normal distribution, for hypothesis testing, we always use just true. That would give you the area. That would give you the area all to the left of 2.5 as the distribution. So click. That's 99.37% or 38%. So it's approximately equal to 99.38%. Right? So this is your actually the answer to this question. What's the probability that so this is answer to this question. What is the probability that they make, it was less than, right? Less than $12,500. Now, if the question says exactly the same question, and let's say this question says same question, and instead of less, let's say it says more than. More than. If it says more than, right, It's the same calculation, but it's the opposite. It's actually the inverse, right? So it's a 1 minus. So equals to, let me just copy this one. And we use the same thing, just instead of less than, we have more than. More than, that would be 1 minus less than, and that would be 1 minus 0.9999, 0.9938.
Is that supposed to be more than or less than in the parentheses there?
This one is more than. If the question is saying more than, right? The second part. And then more than means 1 minus less than.
Okay.
It's the opposite. So that would be 1 minus point. So you can also calculate that easily. So that's equal to 1 minus 0.9938. And that would be 0.0062. Okay. So later you will see that this opposite part will be your p-value, that small part. The big portion is your confidence level. The other opposite is your p-value. So let's just close. I hope this works for you. You will, I can say, never use these calculations during the semester. I'm just trying to remind you of how these calculations work. Okay, so let's continue. So you can answer to these questions as well in the same way, just change the numbers. And there are more examples here to practice. So what is a point estimate? So a point estimate is the statistics or statistic or single value computed from sample information, which is used to estimate the population parameter. The example of a point estimate is average, right? So the population has an average. So when we say a population parameter, in your mind, the easiest way to remember this is just say, okay, population's average versus sample's average, right? So that estimate is coming from the sample we take. We take a sample and we calculate its average. So this versus the population's parameter, right? So that's the question. So a point estimate is a statistic like average computed from a sample, which is used to estimate the population's parameter. So using the sample mean, we're going to estimate the population mean. Why do we do that? Most of the time it's because we don't have access to the population. In most surveys, not everyone is interested to answer your questions. Not everyone's answers are accurate or correct. So as a result, selecting a sample is actually wise. Or maybe it's very costly to get everyone's information. So a confidence interval estimate is a range of values constructed from sample data so that the population parameter is likely to occur within that range at a specific probability. The specified probability is called the level of confidence. Okay, so let's explain that, because I know just looking at a definition is not easy to understand what confidence interval is. So confidence interval or interval estimate is a range of values used to estimate the true value of population. This is another way of explaining it. The confidence interval is a range of values used to estimate the true value of the population. So in fact, we're going to talk about the estimation of population. How far are we from that population parameter, right? When you say 95%, that means you can have like 95%. You can calculate a range. So that range can be 2 times standard deviation. But when it comes to a sample mean, of course, the formula changes. It's not 2 times standard deviation, but when we say 95%, so 2 times standard deviation away from the mean would actually, there's a probability that Any other sample you take, 95 of them would have a sample mean in that range. Distribution, what would be the z-value? 1.96. So 1.96 is associated to 95% confidence level, okay, or 5% significant level. So this is a good example of confidence interval. So you can see that here we have for 95% confidence interval about 95% of similarity, and these intervals, smaller intervals, these are your samples, right? These are your samples. They're a smaller sample. Do you remember the sample of 2 for sample mean? Let's see, first sample, second sample, third sample, fourth sample. So you can get like 100 samples here. If you have 100 samples, when we say 95% confidence, what do we mean? 95 of those 100 samples I selected here, 95 of them include mu. Is that happening? So if mu is in 95 of those 100 different samples I selected, of course the samples are at the same size. If one is 2, all of them are 2. 3, all of them are 3, right? So you select samples of the same size, 100 different. And you want to see 95 of them, you want to make sure 95 of them include mu in that interval. So the first one, does that include mu? Yes. Second one, does that include mu? Yes. The third one, yes. Fourth, yes. Fifth, no. Right? So let's say 5 out of 100, they don't have to include the mu in the interval, but 95 others, they include. That's what we mean by 95% confidence, meaning that if you select 100 samples similar to the first sample, that range that you selected as a confidence level, that range includes, 95 of them include the value of mu or population's estimation. So how do we calculate the upper bound and lower bound? This lower bound and this upper bound based on our x bars, right? So there's a formula, x bar plus minus z value. And where does z value come from? The 95% or 99% confidence is given to you. You can calculate z based on that. Sigma is given to you, and sample size is given to you. So you have the sample size, you have the standard deviation, you have the confidence level required, which is 95 or whatever. You have the x bar. You just substitute the numbers here in this formula. You find the upper bound and the lower bound. It's easy as that. So here we have an example. American Management Association wishes to have information on the income, right? Income of the managers. So average is 45,420. How many managers did you select? 256. What's the standard deviation? $2,050. So what's the range that we can say like 95% of these managers have salaries in that range? So we can simply just calculate it. So X bar, that's the average salary, plus minus. So we say 95%, right? And earlier we showed you that we can actually calculate the 1.96 is a z-value associated to, z-value is associated z-value to 95%. So 95%, z-value for 95% is a two-tail, is 1.96, multiplied by standard deviation is given, divided by radical, sample size is given. Substitute the numbers, calculate the plus minus. So plus will give you the upper bound. Upper bound is 45,671. Lower bound is 45,169. What does that mean? What does that mean? How do we interpret this? So this is how we interpret it. If we select many samples of 256 managers, we can select like thousands of it, right? And for each sample, we compute the average and construct a 95% confidence interval. We could expect about 95% of these confidence intervals to contain the population's mean. In other words, about 5% of the intervals would not contain the population mean annual income. So this range, in fact, includes 95% of salaries of these managers, right? So we know that 95% of our managers, they earn salary in this range. So if you are an accountant, if you are a top manager or general manager of this company, and you want to decide to increase or decrease salaries or hours of work, you can decide based on that, because you know that 95% of your employees, your managers, they actually earn in that range, right? 5% of them may not. Maybe they earn less. Maybe they're new, they earn less, or maybe they're top managers and they earn more. So, but anyway, we know that 95% of them, they earn in that range.